Howdy, folks. It's day 73, and it's the introduction to the most important concept in all of chemistry, maybe in all of science. Well, kind of, besides entropy. Hey. The target of today is to understand a thing called Le Chatelier's principle, huh? Le Chatelier, a brilliant Frenchman, which we'll get to know pretty well. One of the key things that you should notice, of course, is we don't have to pick up that stuff, but vanilla ice. Or a better song, Now Bust a Move. Ooh, love that picture, Finney. Miss that little guy. Yeah. Let's see if you can bust a move on this like good old Finney. Take on a little problem like this. Don't be afraid to practice your skills. And then tell me, what is the KQ of this equation? So pause it, try your own attempt at it, see if you get it right. But be careful. Cool, let's swing at it together. If we look at this, of course, first thing I want to notice is it's asking me for a bunch of stuff. It wants to know what are the concentrations of D and E at equilibrium of this fictitious reaction, right? So first thing I do is I write down, of course, D plus 2E makes and breaks F, and it's a reversible reaction, so it can reach equilibrium, as all reactions can, right? If we look at this, one of the things that we should notice, I can easily solve this. I could use an ice chart. E standing for equilibrium. And then I can figure out what's going on. I got my initial, I got my change, and I got my equilibrium concentrations. Does it give those to me? No, not right off the bat. You should recognize that these are just for concentrations. So that means I have to take these and find the concentration of D initially, which I can do because it tells me that I got 0.80 moles of D in every 2 liters. So it's 2.0 liters. That means it's actually a concentration of 0.40 molar D. Right, that's what it's starting off initially. If I look at my E, it does give you the info you need. It tells you that E is at 1.60 moles of E. It's a bit of a pile, right? Mile and a half and a bit. Divided by, of course, the 2.0 liters to make it moles per liter. That would give you a whopping 0.80 molarity of E. And then if we look at the F, the only F they're giving you is they're giving it at equilibrium, which they typically do in this type of problem. That, of course, is 0.60 moles of F, but that's in the same 2-liter jug that's being made in that thing. So that comes out to the 0.30 molarity of F. Now, those are molarities. That's what I can plug into my ice box because the ice box takes solutions, like you put sodas inside of an ice box, right? Put it in the ice box, dear. Now, if we look at D, of course, we know the initial. It's 0.40 molarity of the D. And we know that the E was 0.80 molarity of the E because we just plugged that in, right? Then, of course, it tells us that we know it's 0.30 molarity of F when it's at equilibrium, crucially, right? So one thing I could notice is that reaction hasn't started yet. So there's absolutely, you can assume there's no F that's been produced yet, right? It's the convenience of this thing. Hey, it's definitely changed because it went from 0 to 0.3, so that's adding 0.30 that was created of F. That's my change. F and D are at a 1-to-1 ratio, so I can subtract for every F I make, I destroy another one, so that's minus 0.030 of the molarity of F. If I take that away, I'm left with 0.10 molarity of the D, so easy it hurts. Then I can see I destroy twice as much of E for every F that I create. So that's, of course, 2 times the 0.30 molarity of change for my E. So that comes out to, 0.60 that I'm taking away from this because I'm destroying it, which leaves me with only 0.20 molarity of E at the end. And look at that. I found my equilibrium concentrations of D and E, and that was so easy it hurts. Then I could take that and go a step further and say, okay, find me the KQ. That's what I did, right? That means that I want to write an equilibrium expression. We can assume that these are all solutions just because we're making it easy. They have concentrations to them, right? So that, of course, would mean that the F would be on top being my products. We'd have a little bit of D and a little bit of E, and the E would be squared, right? Then I can plug in my numbers for those things because I have the concentrations. But remember, this is only for the equilibrium concentrations because it's a KEQ. So that would be the 0.30 molarity of the F on top. D is the 0.10. And then I can notice the 0.20 squared. Hey, that makes a pretty small number, right? If I solve the top and the bottom separately, 0.30 will now be divided by 0.004. And that's a dead giveaway for the kind of KQ you're looking at. One thing you notice, that's a really whittle number, and that's relatively big next to it. So that means this is going to end up with a big old number like 75. and 75 is a big number for the KQ. Anything greater than 1 is a big number for it. That means at equilibrium, this thing favors a whole lot of products, right? And there's lots of products, and compared to the reactants, there's 75 times as much of the products. So this thing favors the forward reaction, but we can see that at equilibrium, it's still, of course, making and breaking it at equal rates. It just favors making more of the products when it does that, right? One analogy you can think of this is kind of like eating chocolate, because usually this is love is a verb week. And if you eat chocolate, there's this cool thing it produces inside your body called, oxytocin. And that's just basically chemical love, right? Dopamine's the other name for the other neurotransmitter releases. That means that if you eat a little pile of chocolate, it favors a whole lot of love, right? Not that you're a chemical reaction or anything. You just, you love the chocolate, so you eat more of it. So you reach an equilibrium unless you eat too much of it, right? I can also turn this into an energy diagram, because you'll be thinking about that as we go through this. One thing I can see here is I got to decide if this thing is a forward reaction that's uphill or downhill. Well, one thing I know, it likes making products. So that means the universe sure does enjoy downhill battles, because that's going to leave you with more products than it is reactants, because that's an easier path to go. It has less activation energy to go in that direction. So that means that this reaction favors the forward reaction at equilibrium, because the forward reaction is exothermic. It takes, of course, less activation energy to go that way. A lot of information, a little bit of piles and stuff. Hey, that looks like claim evidence and reasoning. Chocolate. Now, get out your notes, because you already got them out. Woohoo! One thing we're going to look at, of course, is one of my favorite demos that we don't get to actually show you, but I'll have a little video of somebody else doing it. And it's this neat thing that looks at basically making a reaction do what you want, which is the key of le Chatelier. That's the French. We've got on one side of this pinkish stuff. It looks red in this, but it's pink in reality. And that's called cobalt ions that are surrounded by a whole bunch of 6 waters, right? It's in solution. That can be converted, if it bumps into chlorine, into this stuff called cobalt chloride ions. That is a nice, brilliant blue in color. That's our products, right? Our reactants will be this pink color. It's red on my screen so you can see it. These, of course, are my reactants. So I can, of course, do this back and forth, because that's going to produce the water, it's kicking them off. Now, if I'm going to figure out and monkey with this and make it do what I want it to do, first thing I want to think about is energy, right? And if we look at this reaction, one thing I can see is heat is a reactant. So it needs heat to go forward, which means if you got to add heat, that's an uphill battle, which means that, of course, these are my reactants, these are my products. This direction is going to require the addition of heat to go in that way. So that means that the forward reaction is endothermic, which also means that it's easier to go back the other way. So the reverse reaction is exothermic. Hence, it releases heat when I make cobalt ions. I break up cobalt chloride. Now, that's what the universe wants to do, but I'm a chemist. I want the universe to do what I want it to do, right? At least for a time. So I'm going to do some things to it. Normally in class, I do the most dangerous demo I do the whole year. I would take and I would add to this 12 molar, usually work with 1 molar, 12 molar of face-off, right? Hydrochloric acid. Now that means that when I add that, what I'm actually doing is I'm increasing the number of reactants. And as soon as I do that, this weird thing happens. As I drop in the hydrochloric, it suddenly turns blue. It was pink. Which makes sense, because if I increase the number of reactants, I'm adding more chlorine ions with the hydrochloric. That's going to increase the number of reactant collisions. And more collisions of reactants is going to make more products. That stresses out the reaction, because there's too many reactant collisions, so it destroys some of them to make the products, and the stress goes away. Oh, ça c'est bien, right? Now, the other part of this, of course, is now it would be a nice blue color. But I wanted to do what I want. So instead, what I'm going to do, and normally would do, is I add a whole bunch of just pure water, right? Dump a bunch in. And water is on this side, so that's a product. If I increase the products, that means it increases product collisions. If the water is run into this, that means it's going to kick off the chlorines, and suddenly it will turn pink. And it makes more reactants. It makes more cobalt ions, nice pink things. Cool. I can shift this by changing something. All I changed was my concentration of reactants or products. Hey, that's one way to make a reaction do what you want. But that's boring. I could also change something else. Here I've changed the concentrations of reactants or products. I could also change energy. right? If I change the energy, the easiest way to do that is I could take this, and now that it's turned a nice pink color, because that's what it would be at this phase, I could take that same little tube and I could add heat to it. And when I add heat to it, what's heat make things do? It makes them move faster. That increases the amount of collisions of both reactants and products. And the universe is like, whoa, that's too many collisions. You're stressing me out here. The universe hates stress. That's why we hate it, and we're lazy. So if we look at this, adding those extra collisions, the universe does the most intelligent thing that it does without thinking about it. It reduces the stress because if you add, it moves away from it. What it does is it will always favor, if you add heat, it will favor the endothermic reaction because that does a cool thing. It stores the heat in chemical bonds. It had too much energy moving, kinetic energy, so it stores it in potential energy, chemical bonds, and does that for a simple reason. If it stores it in bonds and put things together, there's less particles, so that means that would reduce the number of collisions. Notice I heated it up to make more collisions, and so it reduces the number of collisions by storing the energy in bonds. How elegant. It's running away. Just like the French, if you add, it run away. Ça c'est bien. Le Chatelier, right? If we look at the part of this, of course, that would turn it from a nice pink color. As I add the heat, it turns a brilliant blue color, cobalt blue, right? Awesome. But if I can add heat, I can also take heat away. And what I would do is I would take the tube and I would stick it in an ice bath. When I stick it in the ice bath, it feels cold to the tube because it's stealing heat from it. And if it loses heat, then that reduces collisions. And the universe is like, dude, that's too few collisions. There's just not enough collisions. So what does it do? Well, if it does that, of course, if you take away heat, then it releases heat, which means that it's going to favor the reverse reaction. It's going to favor the exothermic reaction. It's like you take away the heat, so the universe allows it to make more heat. It pops it out of its bonds. And that's what it does. It's a simple rule. If you take, it moves towards. It's like if you take a Frenchman's baguette, they will go at you. They will move towards you. But if you add Germans, it will run away. Yes, I know. World history. It's like it's equilibrium or something. Yes. So if we look at this, of course, this releases the heat energy by doing a simple thing. You didn't have enough heat, enough collisions, so it does it by breaking the bonds. It breaks the cobalt chloride apart and makes these cobalt ions that then just go into the water. So breaking the chemical bonds releases the potential energy and turns it into kinetic energy, and it starts moving so that you have the right number of collisions. You basically reduce the number of collisions by chilling it. So the universe does whatever it has to increase the collisions. And the easiest way to do that is to favor the exothermic. You should notice that it would do this for a time until, of course, it reached a point where the number of collisions was just right and it was balanced, and it would go back to being at equilibrium. Now, in this reaction, of course, one thing I should notice is it definitely has trouble making products because it's an uphill battle, but it will be able to, of course, shift back and forth, and I can force it to shift. One of the ways I can shift it is by changing concentrations. The other easy way to shift it is what you do when you cook. It's why you cook. You change the amount of heat energy or any form of energy, and that can shift it temporarily as long as the energy is there, right? Cool. That, of course, is much better when you watch the video. Here will be the classic tubes. There's the cobalt ions, nice and pinkish, and there's the cobalt blue. And then, of course, the cool thing is I can take it and add the hydrochloric acid to it, which makes it shift to blue. And then I can come back and I can add water to it, which then, of course, turns it back to pink. I'm basically simply just adding, and it's moving away. This beautiful concept is the one that we need to conquer today, and it is the most important. How do you get a reaction to do what you want? Well, ask this fine gentleman. This is Louis de Le Chatelier. And he, of course, was one of the Frenchmen that was the originator of the best way to look at chemistry and get it to do what you want. And like a true Frenchman, he hated stress. So that's what it's about. Le Chatelier is principal, if we say it correctly. Le Chatelier, is the correct way to say it. It's pretty simple. If you put stress on an equilibrium reaction, or any system, the reaction will shift to relieve that stress. If you stress out the universe, it does whatever it takes to reduce the stress. And typically the stress we're talking about is collision. Right? So if I add something like reactants to make more collisions, it will move away. If you add the Germans, the French, they run away is a good way to remember it. It just happened in a couple world wars. Then, of course, you can take the Germans out. And when you do that, the French move back towards it. Oh, very nice. Désolé. Now, cool thing about this, you can shift a reaction by changing a couple of things. One of them is easy. What am I adding? I'm adding either products or reactions or taking them away, which changes the number of times they collide. So, easy way to do that, of course, would be to change the concentration. Adding concentration makes more collisions. It shifts away from that reactant or product that you added. Temperature, of course, is affected by heat energy. Heat energy makes things move faster. Temperature measures how fast they move. So if they have more collisions, they'll do whatever it takes to have less collisions. If you take away the collisions, the universe rips apart bonds to make collisions. And then the other one that's tied to that, of course, is pressure and volume. If you put something in a smaller space, then it's more likely to collide, like the bumper cars we talked about in gas laws. So it'll favor whichever side has less particles, because less particles will equal less collisions. Hey, I wonder why there's a piston in your car that takes and reduces the amount of space, so it can increase the number of collisions that are going to happen in that. Hey, it's shifting equilibrium. Le Chatelier! Say it with me now. Le Chatelier! Add away, take towards is the easy way to remember this. Now, we're going to explore this, and you're going to explore it on your own using this beautiful PhET simulation that we explored a little bit when we looked at equilibrium. Now it's the time when it really shines, because you can monkey with reactions and make them do what you want. So let's show you how you do that. If I look at this, what I'm going to do is go to the many collisions part of it. And you can see that I've got it set up. You can see that this is a reaction that's an uphill. So this is an endothermic in the forward, but it can go backwards and forwards. And I got a nice little bar graph that's in here. So what I'm going to do is I'm going to add 50 of each of the reactants, right? And let them start colliding. And when I do that, boop, 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 look at what they're doing there. They're starting to turn reactants into products, right? And as they do that, the cool thing about this is I can see that it's, well, what is it doing? Oh, it's kind of keeping the concentrations pretty close to the same. It's reached equilibrium. Now, how can I mess with that equilibrium? Well, I can look at my strip chart and notice that when I do that, of course, I can see that they're reaching their own equilibrium as they do that, right? There we go. They're flattened out in their concentration gradients. I like the bar graph when we're thinking about it, but the strip chart is a very handy tool. If we take this, one way I can shift it, I could add more reactants, right? If I add double the amount of reactants, say 100 of those things, they're more likely to run into each other. And what would that do? As they run into each other, they start to collide more often, and that causes them to shift. And when we look at that on our bar graph, we can see that, now I'm starting to make more and more of those products because the reactants are colliding more often. If I take and I pause it, I can more easily manipulate those. Let's try that. And boom, look at this, more collisions. Hey, it's like serious bumper cars, and that definitely shifts it to make more products. You can see it's shifted the equilibrium, but only temporarily, and then it would turn to the same ratios. But the way I can do it, of course, permanently, is if I take this, I reset all those things, right? Yep, reset them. Here I'm going to throw in 50 and 50. Boop, boop. And when I do that, boom, they, of course, will start to collide. As they collide, you can see that it's starting to shift. In my strip chart, I can see that they are moving towards an equilibrium. You can see that this one does not like to make a lot of products because it's an uphill battle. So one thing I can do is I could increase the temperature. If I increase the temperature, notice that green total energy line starts to move up. And if it gets above that line for the products, it's much easier for them to collide hard enough to make the products. And look at what's happening to the strip chart. The strip chart is starting to shift the position of equilibrium because I added energy to the system. Thanks, buddy. If we look at this, as it shifts the energy of the system, it causes it to change its KEQ. Because one of the few things that actually changes its equilibrium position is the energy. I'm adding heat. That's too many collisions, so it's reducing the number of collisions by storing it in chemical bonds. If I continue and raise my heat above this, then it becomes just as easy to go back and forth. And when you do that, you'll notice that, hey, look, its equilibrium position is closer to an equal ratio, right? It's not perfectly equal because, of course, this is still an uphill battle. How else could I change this? Well, the cool thing is you can do rate experiments, and in the rate experiments, you can change other things like the activation energy of these. So what I want you to do, of course, is try monkeying around with those. You can see that with those, you can change things like, the activation energy. The only thing you can't change here, which is kind of annoying, and I wish they would change it, is the size of the box, because that would allow you to change volume, which can change, pressure. Oh, the number of collisions, because that's what pressure measures, right? So try that out on your own. Of course, I want to bring you back to the idea of this. Long time ago, we did shake them ions. We were looking at saturated solutions before this whole COVID vacation started. And the neat thing is I built some crystals because I'd saturated the solution. And if you watch carefully, you would notice that some of the ions would attach to the crystal and then pop off of it. And then attach to the crystal and pop off of it. What are they doing? Well, they're making and breaking at the same rate, because when they reach saturation point, they're at an equilibrium at that temperature. Of course, this one would have been nice if you could change the temperature of it, but that's what the new FET is for. Now, you should explore that FET. That, of course, is using the one that's rates and reactions, and see what's going on inside of it, monkey with it, see how you can shift it. And always think as the Frenchman, Le Chatelier, whose principle was pretty straightforward. He basically had two rules to this. The universe hates stress, right? So if I add stress, the reaction will do whatever it takes to move away from that stress. If I add reactants, it will destroy the reactants to turn them into products so that there's less collisions of reactants, right? No, more products. If I, of course, do another thing, if I take reactants, then that means that there's less collisions of those reactants. So the universe will break products and favor the reverse to create more of those reactants to make sure that the number of collisions stays at equilibrium, which is where the equilibrium term comes from, making and breaking at the same rate. Ultimately, the things that can shift that are things like adding heat energy, right? You can, of course, change the concentrations of those things to shift it temporarily, and you can also change the pressure and volume, which is why we did gas laws first. So, remember, le Chatelier, if you add, it run away. If you take, it moves towards. And never take a Frenchman's baguette. It'll come straight towards you.